left off talking about this concept of independence or independent events, and the idea was, sometimes, like we saw, like with the Cokes and the lemonades, it's like one trial affects the next trial. Sometimes that's not the case. Like if you flip a coin, no flip affects the probability of the next flip. So independence occurs when the outcome of one doesn't affect the probability of another. And you can check for independence. It all comes down to conditional probability, because what you can do is you can compare the overall probability of an event to the conditional probability of that event given, some other information. And if the conditional probability changes, it's telling you that knowing the condition changed the probability of the outcome occurring. So like we looked at some examples like kings, hearts, and reds. Some of those events can help inform the probability of other events. The thing about kings, though, is kings are pretty much independent from hearts and red because there's the same number of kings in every suit, same number of kings in every color. So we looked at the conditional probabilities, and what we found out is that if you tell me it's a heart, it doesn't affect the probability of a king. If you tell me it's a king, it doesn't affect the probability of red. So being red and being a king are independent, being a king, being a heart are independent, but these are not, because if I tell you it's red, it changes your probability of pulling a heart. Or if I tell you it's a heart, it makes it guaranteed that it's red. Those would be considered dependent. Okay, then I was showing you, we had already done an example where we multiplied probabilities to calculate an and probability. This is just the general multiplication rule, and it says that if you have the sample space, like if I have a contingency table or I know what it looks like to draw cards, like I don't need to use formulas to calculate an and probability. Like what's the probability that it's red and a king? I could figure that out because there's 2 red kings, out of 52 cards. But if you have to go down the formula, you have to consider conditional probabilities. So the general multiplication rule for calculating and probabilities, it looks like this. And I showed you a way to use that with the texting and drivers one. I think that's kind of where we left off. Yeah? The key is tracking down, okay, what are we looking for? I'm looking for an and probability. Okay, I know I'm probably going to have to multiply 2 together. So then it's like going back through the problem and identifying, well, one of those is conditional. What was the given condition? The given condition was not texting, so we should be multiplying that by the not texting probability. This is actually extraneous information. We didn't need that number. So, all right. You don't necessarily need that, though, if you have independent events, because like we saw in our last example, that kings and hearts are independent. Now this one we happen to have the sample space. What's the probability that you get a card that's a king and a heart? All right, well we don't need a formula for that necessarily. It's just what? Well, there's 52 cards, and how many of them are kings and hearts? There's only one, right? But if you notice, the probability of getting a king, right, was 1 out of 13, and the probability of getting a heart was 1 out of 4. And so the probability of king and heart is exactly the probability of king times the probability of heart, right? So in this case, but neither one of these is conditional. So why does it work here, but it didn't work in the texting problem? Well, like, for example, on the texting problem, right, to find the probability of being over 40 and not texting, we couldn't just take the probability of not texting times the probability of being over 40. We didn't just multiply these 2 together, right? It's not P of n times P of O. We had to take into account the conditional probability. But if you look at it here, the probability of K and H is exactly the probability of K times the probability of H. There's no conditional probability involved. Why? Like, how come here I can just take the probability of one times the probability of the other, but this one was like way more complicated? Why?
Because it's independent.
It's because they're independent, right? And the reason it works, the reason you can take that shortcut is because K and H are independent. So that's the key, right? So the general multiplication rule says that if you want to calculate an AND probability, you're going to multiply probably, but you're going to have to figure out what probability is conditional if they're dependent. But if two events are independent, you don't actually have to worry about that. To calculate the probability of A and B, you just take the probability of A times the probability of B. So it's like this, there's a special multiplication rule. Okay. So it's kind of like before with OR probabilities, it's addition, but you might have to subtract the intersection if they're not mutually exclusive. And probabilities, you have to multiply. It's complicated if they're not independent, but if they're independent, it's easy. If they're independent, you just multiply two probabilities together. So, okay. All right. Some of these problems can be made a lot simpler, though, if we learn to count, which sounds really dumb because everybody knows how to count. But counting can be complicated, and that's what I want to talk about next. I split it into two slides because the slides start to get really big, like file-wise. I did record it. Yeah, we're good. Okay. So I want to spend a little bit of time talking about how to count. And did you guys do counting in Math 50 now? I don't know if they even do that in Math 50 anymore. Is there counting involved, like permutations, combinations, stuff like that? Interesting. Okay.
Permutation and that.
Okay. So some of this may be review, some of it may be new stuff. So I'll show you what I mean when I'm telling you how to count. So I'm going to show you how to do some counting strategies first, and then I'll show you how you can use them with probabilities. Some of those complicated problems can become a lot simpler. So here's an example. If you look at standard Washington license plates, you got 3 letters and then 4 digits. And assuming you can pick any 3 letters and any 4 digits, I'd like to know how many unique license plates can you form in Washington State? What do you think? How would you solve it? Anybody got an idea? What do you think? So one way you can do counting problems is you can kind of you can draw little slots and think about, okay, well, how many ways can each of these things happen, right? So it's like, for example, if I'm thinking these got to be letters, right? And then these all have to be digits. Okay, so then, well, for my first letter, well, how many ways can my first letter, how many letters can I pick? 26. Yeah, it happens. It's somewhere in the ballpark. So there's 26. So there's 26 ways you could pick this letter, right? And there's 26 ways you could pick this letter, and there's 26 ways. I'm assuming there's no restrictions on license plates. I'm assuming you can just put any letter in any spot. I don't know if that's true or not, but let's say it is. Okay. Then what about, so these are A through Z. What about the digits? So how many digits could I drop here?
10.
Yeah, there's 10 ways I could drop. I could choose that, but then I could pick another 10 there and another 10 there and another 10 there, right? So each slot has a lot of different ways that you could pick it. So then together, they interact a lot of ways. In fact, how many ways? How would I find the total number of ways, do you think? Yeah, this is what I was talking about when we did the dice. It's like, the first dice is 6 ways, second dice 6 ways. So the ways they can interact is 6 times 6. In general, if you have a bunch of things that can happen and you want to see how many ways they interact, you just multiply. So the answer would be whatever 26 times 26 times 26 times 10 times 10 times 10 times 10 is. What is that? It's pretty big. A few million. Like that?
Yeah.
Is that true?
Yeah.
Okay. So 175 million 760,000 unique possible plates that you could form using that structure. Yeah? Okay. This is like this is like a really, really gigantic tree diagram, because you could think like the first plate is like there's 26 branches, but then each of those branches split off into 26, and then each of those split off into 26, and then each of those split off into 10, right? So the tree diagram just like blows up into 175 million branches. So you would never draw it. But yeah? Seem reasonable? So in general, this is called the basic counting rule, right? So if you have like two or more events, let's say, two or, the parentheses should have been there. So two or more events, which, let's say, can occur, say, m and n ways, respectively. Then the number of ways they can occur together, m times n, so m times n ways. So you just multiply. Okay, I don't know why I'm squaring that. It's not really an answer, but okay. So basically, the point is like if you're considering multiple things interacting, if this thing can happen this many ways and that thing can happen that many ways, then the number of ways they can interact is just the product. Okay. That's the basic counting rule. And if you have a problem like the license plate example, especially there's something sort of special about the license plate problem. In the license plate problem, you can repeat numbers and letters. It's not like once you use it, you can't use it again. Okay. So this right here, I'm going to go back here and just mention something, right? The fact that repeats are allowed. This is sometimes called, we would call this with replacement. In other words, it's like the reason we call it that is because it's like if you think about drawing them out of a bowl or out of a hat, like a lottery number, it's like you pull it out, you look at the number, and then you replace it back into the pot, and you can pick it again. Okay, so repeats are allowed. That's not always the case. So in this case, it was. But if you're in a situation like license plates where things are allowed to repeat, this is pretty much how you have to approach counting problems. There's not really a much easier way. But sometimes that's not the case. So sometimes it doesn't make sense to have repeats. So let's say, for example, I have a box, and in my box I have a bunch of textbooks. So let's say I have 12 of them, and I want to put them on my shelf. So what I want to know is, how many different ways could I rearrange my 12 books? So what do you think? So if we go back to the strategy we were at, if I got one, you think about having 1, 2, 3, 4, 5, 7, 8, 9, 10, 11, 12. I got 12 spots on my bookshelf, right? Well, when I go to reach into my box, okay, well, how many books could I put here? 12. How about here? See, in this case, it wouldn't make any sense to throw the book back in the box and pick it again. So once you pick one of the items, you actually have less things to pick from. It's kind of like the Coke and the lemonade problem, right? So once I fixed that book in its first slot, now I'm down to 11 books, and then I'm down to 10, and then all the way down, right? Every single time I have one less book to pick from. Until at the very end, it's not even like it's just one. There's only one to put there. Yeah? So then what's the number of ways that I could do this? Yes. There's a shortcut, but if you didn't know the shortcut, you could still get the answer. You could just multiply them. Right? So 12 in the first, 11, 10, 9, 8, all the way down. What does that come out to be? By the way, somebody do that for me. It's still a lot.
Can you do it with like the 12th and then the exclamation mark?
Yeah, so this is the pattern here is actually called a factorial. I'm going to talk about that in a second. But what does it come out to be? 479,001. 600, like that? Okay. So if I want to rearrange 12 books, I could do it 479 million ways. So that's a lot of ways. All right. What happens is you see this pattern a lot. This pattern where you're taking, one, it goes down by one each time because what you're doing is you're pulling it out of the pot and you can't pick it again. So because we see this a lot, in math we have this function called a factorial, and it shortcuts that. Yeah.
I didn't know you can't choose again if it doesn't ask you a question.
Well, sometimes you have to just use.
Like to me, I would rearrange it, and you could put the same one in because I understand that. That's what I was thinking too. Like if you were to put 12, 11, 10, whatever, then you could put 1, 2, whatever, and then keep rearranging it.
Yeah.
Well, that's true. That's true. But the thing is that, see, here, this 12 right here, this 12 takes into account that you could put any single book in that spot, whichever one you want. So you can start it off with any other book, whichever book you want, right? But once you pick that book and you throw it in the slot, right, it's fixed, Because in the tree, you think about it like a tree diagram. See, and I don't really want to draw it necessarily, but, we can start it. So it's like there's first you could pick from 12 or 1, 2, 3, 4, 5, 6, 8, 9, 10, 11. It's nasty, but you can A, B, C, D, E, F, G, H. Right. So let's say that's not what I want to do. Whatever. There's a menu down there. It wants to pop up, but you get the point, right? So it's like in this case. You could pick whatever book you want in the first slot, right? But then if I'm going to go off of this branch, like say I put H in that slot, right? Well, I can't pick H again, and so then from here, I'd only have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 choices. A, B, C, D, E, F, G, H, I, J, K, L. But I didn't eliminate the possibility that I didn't fix H in that spot. You could have gone down any of these other branches that had not H in the front. You see what I mean? Whereas with the license plate example, that's not the case because if you go, the digit spot's easier to consider. 0, 1, 2, 3, 4, 5, 6, 7, 9, 0. Right? You can split there, but then what happens on the next branch? You can also pick 0, 1, 2, 3, 4. You see what I mean? 6, 7, 8, and 9. So in the license plate example, every single branch in the tree goes out by 10. 10, and then they expand by 10. But here, it doesn't work. This expands by 12, so you still have every possibility in the first spot, but then the next one can't expand by 12 because I can't pick that book again. The next round's only going to expand by 11 branches, and then the next round of the tree is only going to expand by 10. Right? Yeah.
So in the license plate, you could have a combination of 0, 0, 0.
Exactly.
And then 8.
Exactly. Yeah. So it's like on my shelf. I can't have my calculus book, then my statistics. I can have my calculus book, my statistics book, and my algebra book, but I can't have calculus book, calculus book, calculus book because it only exists once. Yeah, in the license plate example, you can have 0, 0, 0 on your license plate. So, yeah. Yeah. So this would be an example where we would say that you have to do it without replacement. Now, there's nothing particularly. I wouldn't say that there's anything particularly obvious about this that makes it with or without replacement. It's sometimes it's just something you kind of have to deduce by thinking about it logically. Does it make sense to be able to pick the same book twice. It doesn't make sense, because otherwise what would I be doing? I'd just be picking it up and throwing it back. I'd never be filling up my bookshelf, right? So when you're actually picking physical things, typically you're going to be doing it without replacement. Or if I'm sampling people out of a population, I'm not going to sample you and then throw you back into the pot and then allow myself to sample you again. I don't want you twice. I want someone else. All right. So this pattern, though, where it goes down by 1 each time, these are called factorials. So what we saw there, that 12 times 11 times 10 times 9 times 8 times, you don't have to rewrite it all again. You could just, because that's really annoying to write over and over, we denote that as called 12 factorial. So the exclamation point right there, it's a factorial, and it tells you to take 12 and multiply it by every single number below it, right? So like 5 factorial would be 5 times 4 times 3 times 2 times 1, right? A factorial would be 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Okay. The thing is that the factorial, there's actually a button in your calculator that you can, pretty much every calculator has it. If you're using the TI-30, the teal one that I like, there's a button in your calculator that says PRB, probability. And if you hit that PRB menu, you'll see the exclamation point is one of your options. So what you can do in your calculator is you can type in 12, go to your PRB menu and select the exclamation point, hit that, and then hit enter. You want it to look like that on your calculator, 12 followed by the factorial, and then hit enter. And if you do that, it should spit out the answer that we got in the last problem. All right? Yeah? Okay. Some other calculators have it in other places. Yeah. Some of them have it as like a shift option or a second option or something like that. But if you have a TI, I think most of them have it in the PRB menu. Question?
I was just going to ask for like the license plate,
Yeah.
how there was only 4 numbers.
Yeah.
And there was 10 available.
Yeah.
How do we do the factorial?
Well, that's not, that one won't, a factorial doesn't apply to that. That's the thing. Because, yeah, what happens here is that if you have a situation like this, you can't use the factorial button.
You just have to manually do it.
You just have to manually do it.
Understood.
Yeah. Mm-hmm. So that's the thing. When when you're allowed to repeat things, when replacement's allowed, there's no real easy way to do it.
Yeah.
You just have to draw it out. This is how many ways, and you just got to put them all the numbers in your calculator. But if you have a situation like this where you're picking things out but you can't repeat, then you can use that factorial as a way to sort of shortcut the process. Yeah. And so in general, the number of ways to rearrange, say, n items is going to be n factorial. So this is assuming you can't. The idea behind rearrangement is like you have a fixed number of items. It's not like you're allowed to pick multiples. So if I have a fixed number of items, I'm trying to figure out the number of ways that I want to rearrange those. It's going to be n factorial. So if I had 10 items, the number of ways I could arrange them are 10 factorial. If I had 15 items, the number of ways I could rearrange them are 15 factorial. If there's 23 students in this room right now, the number of ways we could rearrange ourselves in a line would be 23 factorial. It's like, and factorials get big fast. Because each number you multiply, every person I add in here, so think if I add a 13th, what happens? Now I got to take that big number and multiply by 13. And then if I add a 14th in there, I got to take that huge number and multiply by 14. So they blow up super fast. Yeah.
Can you give like another example other than the bookshelf?
Sure. Here's a fun one. Think about this. Well, we could do this, students, or even it could get worse than that. I don't know. How many people are in here right now? Let's look at the students. 5, 6, 7,
12, 11, 12.
13. Did I count? I don't. How many? I just counted, and I can't. The number I got can't be right. 20 students, and me.
Oh, 21.
Am I 20 or am I 21? I think I'm 20.
21.
One. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, and I'm 1. 21. Did you count yourself?
Oh, no.
Okay, there you go. You exist.
Yeah.
You are important. Okay, so think about if we wanted to know how many ways could we rearrange ourselves in a line. In a line, sorry, and let's say I'm in the, whatever, so let's say line. And there's 21 people in this room right now. Right? So you could draw it out, and you could think about it, like, because there's 21 ways that we could pick the line leader, the special person, and then there's 20 ways we could pick the next person, and on down to the point where, it's fixed, or we could just shortcut it and know that, I know the number of ways we can rearrange 21 objects is 21 factorial. Well, what does that come out to be?
5.10909 times 10 to the
19th?
Yeah.
What does that mean?
That's scientific notation.
Scientific notation. So where's that decimal supposed to go?
19 decimal.
It's supposed to go 19 decimal places to the right. 1, 2, 3. 3 to get to there, and then another 16. So 3. So then basically, right, so boom, 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 right, we got to go 19 decimal places that way. So it's going to be 5109 followed by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 zeros. We'll do our commas. Boom. So, there you go. I don't even know what that number is. Because, well, here's the millions mark. There's the billions mark. There's the trillions mark. I don't actually know what you call them after that. Is that quadrillions? And then quintillions? I don't know. Is that 51 quintillion? I don't know if quintillion's a word. So, but whoever even gets that big, right? So, because by the time you get to billions, you're like, that's like how many people are on Earth. And then, I don't know, it's pretty wild. So, they get huge fast. That's the point. So we could like spend basically the rest of our lives rearranging ourselves in a line. So, which is really interesting to think about. I don't know if we'd ever finish. I don't think we'd ever finish. No, definitely not. Because even if we could rearrange ourselves every like 10 seconds or something, right?
We wouldn't have that much time.
Yeah. Say it took us 10 seconds to rearrange ourselves or something, then you have to multiply that by 10. That's how many seconds does it take. And then you could like divide it by 60, which would give us hours. Divide it by 24, give us days. Divide it by 365, that gives us years. It's going to take a long time. In fact, actually, that's a good. There's another interesting thing to think about. I read about this online, and it is actually true. Think about this. How many ways can you shuffle a deck of cards?
Oh, with the jokers or without?
Let's say no jokers, because who the heck uses jokers? It doesn't matter. It doesn't really matter if you include them or not. So let's say the number of ways to shuffle a deck of cards, right? So we've been talking about cards lately. How many cards are in a deck? 52. So the answer should be 52 factorial. What does 52 factorial come out to be?
8.066 times 10 to the 67th.
To the 67th power. 10 to the 67th. Right? We were already at quintillions, if that's a word, but at 10 to the 19th. That means we have to take that number and multiply it by 10, just like, another 46 times, or 48 times, right? Isn't that weird? So you know what that means, right?
You better get looking.
Everything is special?
Yeah, it does. That means that, so think about this. So do you think that every single possible order of a deck of cards has ever been achieved?
I bet it has.
Think so?
Yeah, because if you think about it, people just shuffle.
All right, well, so think about it this way. Okay, think about it this way. How long have we had playing cards as humans?
Not long.
I don't know. Let's be generous with ourselves.
50 years?
Let's be even more generous. Let's say that we've been playing with cards for a millennia, 1,000 years. I don't even know if we have. Right? Okay, so think about it this way. Let's say that we've been playing cards for 1,000 years. I don't think we have, but let's say. Okay. Now, let's say that cards get shuffled a lot.
Yeah.
Right? Every day. So let's say that think about it in terms of like Vegas or casinos around the world. Okay. So there's like, I don't know, how many casinos do you think there are in the world? Who knows? Lots. But there's probably got to be hundreds in Vegas, maybe thousands.
Yeah.
But let's be generous. Let's say there's like 10,000 casinos in Vegas, maybe. So then, but even if there was like, I don't know, even if there was like 1 million casinos in every country in the world, which there's not. Okay? And there's like 200 countries, right? So that would be let's assume there's 200 million casinos in the world. There's not, but let's say there is. Okay? So let's say that those casinos have been around for the past 1,000 years, which they haven't. Okay? And let's say that they could shuffle, in every single casino, let's say they were shuffling, I don't know, how many decks of cards do you think get shuffled in a casino at a given time? How many decks of cards do you think are on the floor in a casino? A big one.
Probably 50.
Yeah, 100, maybe, even if it was 1,000, right? Let's say that in every single casino, there was 1,000 decks of cards on the floor at any given time, and then how often do you think they're going to get shuffled? Per hour.
100 times.
Let's say per hour.
Oh.
What did you say?
I just said pretty often.
Often, right? Every time a game gets played. Let's say like it's not realistic, but let's say that you could do 100 shuffles per hour.
I'll go more like.
It's probably smaller than that, right? Because they're not actually shuffling them that often, right? The point is it's not going to matter at all. Because let's say they were doing 100 shuffles per hour. Okay? And let's say that we've been doing it for 1,000 years, right? So here's the thing. So 1,000 years is 10 to the third. 200,000 is on the scale of 10 to the, eighth. 1,000 decks is 10 to the third. And 100 shuffles per hour is 10 squared. So even if you had 200 million casinos shuffling 1,000 decks of cards 100 times per hour for 1,000 years, you would only end up with, rules of exponents to add, 11, 14, 16. And I gave ourselves a 2 there. So right? 2 times 10 to the 16th shuffles. So you haven't even made it in that amount of time. You haven't even made it through as many rearrangements as we're going to have to. We're still working on our classroom line arrangements, right? Because that's even less than our classroom line arrangements.
Yeah.
So, and we're not even close, right? Because we could do that for another 1,000 years, and it's only going to get us to 10 to the 19th, right? It's not going to happen. So, in reality, what that tells you is it tells you that most likely, we haven't even gotten close to realizing every single rearrangement of a deck of cards that's possible. So, like, not even close, right? Because the problem is, even if you multiply any number of these numbers by 10, it only gets you up by one factor of 10. And so, it doesn't get you much progress towards 10 to the 67th. So, it's pretty wild. It's even, but so what I tell people when I do this example, though, is it can kind of actually be a good thing, because what it means is that every single time you shuffle a deck of cards, there's a high likelihood that the way you just shuffled them is the first time it's ever occurred in history, like the history of the world, which is pretty cool. So if you're ever feeling bad about yourself, right, if you're having a really bad day, you can like pull out a deck of cards and you can shuffle them, and you could put them back together, you could put them on the table, and you could say, I just made history, right? And you're probably right. There's a high probability that you're right. So, pretty
At
wild.
one point, you were the youngest person in the world.
That's true, I suppose.
Yeah.
Yeah,
Doesn't matter how long you held it for.
I suppose that's true for an infinitesimally amount of time. Yeah. But this one you could do over and over. You could accomplish that like multiple times. It's pretty wild.
Resume builder.
Yeah. 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 Put that on your resume. Anywho, the point is, we got way off track here, but the point being is that if you're trying to look at the number of ways you can rearrange them, you use factorials, but the thing about factorials is they blow up fast. Really fast. So, all right. Now, back to what we were talking about. We're going to run over. We're not going to finish this today, that's for sure. Now, I was looking at the rearrangements. One thing, though, especially when we start looking at sampling, is we're not going to actually be able to probably sample everyone. Sometimes we don't have room for everyone or everything. So, like, let's say I have 12 textbooks, but I only have room on my shelf for 7. So I can only pick 7 books. So my question is, well, how many different ways could I rearrange 7 of those 12 books instead of all 12? What do you think? It should be less than the last one, right? Because I'm not going to have as many to worry about.
The factorial of 7.
So 7's part of it, or yes, but you think about when I go to hit my first book in there, though, it's not. I don't start with 7 options, right? In this case, I'm starting with 12 options still. So I'm starting in the same place. But what happens?
You only go down to 7.
Yeah. Well, technically, I think you'll run out at 6, right? So what happens is I start in the same place, and I start to see the factorial, but then my factorial gets cut off at the end because I'm out of room. So my last 5 books are sitting in my last 5 books are sitting in there, and I can't pick them. But up to that point, I had 6 ways to pick my last book. And you could just do it like this, and you can multiply. I don't, what does that come out to be? Somebody want to do that for me? 3,991,000 and what?
680.
680 ways. Okay. That's the answer, I think, right? Anybody else get that? Just to check. Yeah.
So why did you do it? Why did you times by 62?
Well, so what it is remember I had 7 slots. So I had room for 1, 2, 3, 4, 5, 6. I had 7 books. I don't stop when I hit 7. I stop when I run out of room. And so I would run out of room in the 7th slot. But at that point, I still have 6 books to pick from. Okay, so you can ignore these numbers at the bottom. But now what happens here is it's like a factorial, but it gets cut off at the bottom, right? And so if you'll humor me, I would say you could rewrite this. You could think of this as an actual factorial, but what you're doing is you're dividing out you're dividing out all the rearrangements of the things you can't pick, basically, right? And then, if you think about it that way, this is a factorial, and this is a factorial, right? So it's like that's like 12 factorial over 5 factorial. So the 5 is the leftover when you pulled 7. So you could even rewrite this as couldn't you write it like that? Wouldn't that all be true? I mean, you could. I'm not saying you should, but you could. It's like, if you want to figure out the number of ways to rearrange 7 books out of 12 possible, then, 12 is significant because that's how many books we were picking from, and 7 is significant because that's how many books we were allowed to pick. Right? And it turns out, this is true. This pattern right here, this pattern will always be true. Anytime that you're dealing with a scenario where you're picking a certain number of items out of a total, and you want to rearrange them. So we give this a name. This is called a permutation. All right? So, and permutation is just another name for rearrangements. So if you want to know the number of permutations, in other words, rearrangements, of, say, R items out of N items total, where R is smaller than N. Okay. So we call that the permutations of R items out of N items total. There's a notation we use for that. So the notation we use for that is called NPR. There's a button, you might have noticed, a button in your PRB menu is an NPR because it's a common thing. And the formula, which you can memorize the formula if you want, or you could write it down and use the formula. But you don't need to, because in your calculator, you can find this in that same PRB menu that you found the exclamation point. Okay. So like in your calculator, so if you look at the last example where there was 12 books, that'd be our N, and we were picking 7 of them, that would be our R. So then what we would be calculating, well, we saw, so it's like 12p7. Well, if you were going to do it by the formula, you would see it would be the way that I wrote it on the last slide. But in your calculator, what you do is you just type in 12, then you're going to go to your PRB menu, and you're going to get the NPR button, and then you type in 7, and then you hit enter. So you don't actually have to calculate it by hand. But you have to recognize that it's that type of scenario. It's a scenario where you have a group of items and you're picking some certain amount of them and you want to know how many ways to rearrange it. That's a permutation. So you can check it. Go to your calculator, right? Type 12, then go get your NPR button. Type 7, hit enter. What does it give you? Hopefully it gives you, anybody do it? What does it come out to be?
3991680, the same as the last one.
Hopefully the same as the last problem. It'll get you the right answer. Okay? So it's that special scenario where you're trying to pick a certain number of items out of a total and you want to know how many ways you can rearrange them. All right? You can do it with the basic counting rule. You know, list out the slots and you'll figure it out. You'll get the answer. But if you recognize it as a permutation, you can shortcut it and use the NPR button.
There's like a different one too.
Yeah, we're about to talk about it.
Oh.
Yeah. There's something called a combination. We'll talk about that in a second. Here's one. Here's kind of a similar scenario. So let's say that a Little League tournament has 16 teams. They'll compete. At the end, the top 3 teams will be honored with trophies. First place, second place, third place. How many unique ways could the final prizes be awarded going into the tournament? Right? So essentially what this is asking, what am I really saying here? Is I'm saying how many ways can you rearrange 3 teams out of 16, right? Because essentially what I'm going into the tournament, if any 3 teams could be in the top 3 and any of them could win in any order, this is like with the book problem, except for now I've got 16 books and I can only pick 3 of them to put on my shelf, right? So this is a permutation where N is 16, R is 3, and so I would probably just do it in my calculator. I would just go 16 NPR 3, and if you do that, what do you get?
560.
3,360.
Did you do combinations?
What? Yeah.
It's a permutation.
Oh, it's a permutation?
Yeah.
Oh.
What'd you say?
3,360.
We'll talk about combination in a second. Okay. So that's really, I would just, now, if you want to do it with the formula because you just want to, it's not that hard. Because the formula says this should be 16 factorial over 16 minus 3 factorial. That's the pattern we saw from the one before. And the nice thing about factorials is a bunch of them are going to cancel out, right? Because if you have 16 factorial on bottom and 13 factorial on the top, well, you really only have to follow 16 down until you hit 13 factorial, and then all of those, remember it's like the last one, the last 13 factorials, they're all going to cancel out, everything beyond 13. And so all you really end up with is 16 times 15 times 14, which will give you back to the same answer, which is exactly how it would be if you did the basic counting rule, because there's 16 teams that could win first place, and once someone wins first place, there's 15 teams that could win second, and then there's 14 that could win third. Okay. But the calculator just shortcuts the whole thing. All right? Now notice in these cases, like the order that you finish matters. Like you care if you're first, second, or third. And with the textbooks, I cared about the rearrangements. But that's not always the case. You don't always care about rearrangements. So, I'll show you why. Similar scenario. Let's say that there's 16 students in a class, and I'm going to pick 3 of them to take my survey. Well, how many unique samples could be taken? Now, this is similar to the last problem because there's 16 things, and I'm going to pick 3 of them. But it's not similar because why? It is random sampling.
It's not
Oh,
ranked.
we can replace.
Yeah, there's no rank to your person that I pick. It's not, if you have to go take a survey online, do you care if it's first, second, or third? Do I care if you were first, second, or third? No, you're all taking the same survey, right? So in this case, I don't actually care what order you get picked in. So what happens is, it's like, here's the way permutations work is, let's say I pick student A, B, and C, right? Well, a permutation would, I could have picked A, then C, then B, or I could have picked B, then A, then C, or then B, then C, then A, or I could have picked C, then A, then B, or C, then B, then A, right? Well, so if you're doing a permutation, it says that these are all unique. That's what a permutation says. It says those are all different rearrangements of 3 people. And that's true. It's not wrong. But do I care? I don't care. Because to me, are any of those 3 samples different? They're not, right? All 3 of these are all the same sample from my sampling, from my standpoint. And so what we want to do is we want to collapse these into a single, what we call combination of 3 students, right? It's like, okay, I get it. They are rearranged, and if I cared about rearrangements, they would all be unique, but right now I don't care. So I want to collapse them all into one single combination. Well, how many ways can you rearrange 3 things? Well, it looks like the number is what? I mean, you can count them right there. How many ways were there? 6. But we could have known that in advance because how many ways can you rearrange 3 items? It's just 3 factorial, right? 3 times 2 times 1. Right? So the way it works is, so the way you can calculate things like this where the combinations, you want to collapse them all into single combinations is you can start with the permutation. Because if you start at the permutation would say, okay, well, we would do 16 factorial, and then we would divide by 16 minus 3 factorial. That's what we did in the last example, right? But now what we want to do is we want to come behind, and now we recognize that inside of those 3,360 rearrangements, there's tons of duplicates. And for every group of 3 people I could pick, there's 3 factorial duplicates. So what we're going to do is we're going to divide out all of the duplicates. And so then what we're going to do is it's going to turn into a combination. Now you don't have to do it this way. This is a complicated way to do it. I'm just showing you how it works. So in other words, the red chunk would give us the number from before, 3,360. But now what we're going to do is we're going to come behind and we're going to divide out all those, chunks of combinations that we want to collapse into one. So essentially what we end up doing is we take all the permutations and we divide out, the number of rearrangements, all those duplicates, and then we get a new answer, which is actually, I think, the answer you got before, but what does that come out to be? 560? Okay. Now, that's a complicated way to do it. Don't do it that way. Well, you could, but don't. Okay. This is the pattern, though, and that's what I'm going to talk. So this is perfect. We got just enough time to finish this part. So the pattern here will always change. So the difference here basically is that in the baseball tournament, the rearrangements or the order matters. Like, you want to treat them as unique. But in this example, the rearrangements or the order is not important to me. And so that's when you come across what we call combinations. Okay? So the number of combinations, and by combinations what I mean by that is when the order or the rearrangements are not important. Okay, so the number of combinations of R items out of N total. So you may have noticed if you were looking along in your calculator, there next above N, might have been under it, but near NPR there was a one that said NCR. Okay, so we denote that NCR. The pattern would be that it looks just like the permutation formula, but what you do is you come behind and you divide out an extra R factorial. So essentially you're collapsing all those duplicates into single combinations. Okay, but in your calculator, it's in your PRB menu, just like the NPR was in there as well. Okay. So like if you look at the example that we just did, where it was 16 students, right? So that's our N, and we were going to sample 3. That's our R. So then what we're trying to calculate here is, you could do it by the formula. We're trying to calculate 16C3, but in our calculator, you would just type in the 16, go get your NCR button, and then type in 3, and then hit enter. And if you do that, so type in 16 first, then go grab your NCR button, and then type in 3, and then press enter. What do you get? You should get 560 just like we got before. Okay. So the key is recognizing the type of counting you're doing. It's like if things are allowed to repeat, there's not a special strategy. You just got to do it like the license plate example. But if things aren't allowed to repeat, you just have to ask yourself whether the order is important or it's not important. Okay? And then in that case, you're dealing with a combination. And you could do it like the formula will work. Like if I'm doing 16C3, that's 16 factorial over, 13. You know what? I'm not even doing it. Don't do the formula. Just do it on your calculator. Like, just don't waste your time with the formula. It doesn't matter. But I will show you real quick. Let me draw one more thing for you. This is how I separated out. Oh, I left myself room. So here's the deal. So basically the way it works is when you're counting, you basically have to ask yourself 2 questions. First you have to say, are repeats allowed? right? In other words, is replacement allowed? Wait, I shouldn't have branched that out yet. Oops, okay. That's the first question you have to ask. I'll fix it. So, number one, you say, are repeats allowed? And so if the answer is yes, then you don't really have a lot of options. You just have to go with the basic counting rule. I won't abbreviate that, actually. Basic counting rule. In other words, you're just going to have to, you're just going to have to draw out slots like the license plates and go with that, right? But if the answer is no, say the answer is no, repeats are not allowed, then you have to ask yourself the second question, which is the order important, right? Is the order you pick or get picked important? Right? Because if the answer is yes, then you're dealing with a permutation. You care about rearrangements. And if the answer is no, then you're dealing with a combination. And those are the three main counting strategies. So, repeats allowed, tough luck, you're just going to have to figure it out. If repeats aren't allowed, then you just have to decide, okay, do I care about rearrangements? Oh, yeah, I do. Okay, that's a permutation. Do I care about rearrangements? No, don't care what order they get picked in. Okay, now you're dealing with the combination. All right? Sweet. All right, we will finish. I thought we finished off today. We didn't quite get there, but we will finish that off tomorrow. But I think you have about everything you need for the quiz, so you could take a first shot at it if you want. But it is due tomorrow.